Hello and welcome to the Math Studio. In this video, I'm going to look at another example of converting a set of parametric equations into Cartesian form. This one's similar to the last example in that the set of parametric equations contain trigonometric functions, but unlike the last example, instead of the parametric equations involving cos theta and sine theta, this time around they're involving sec theta and tan theta. However, we can still come up with our Cartesian equation using a very similar strategy to what we did in the previous example. Now, I've labeled the equations, so again, just for the sake of the video, just to save a bit of time, I've pre-written the solution. I'm just going to go through it a little bit at a time just to help you follow what I've done here. Right, so first of all, I've just labeled the equations, our parametric equations. So equation 1, x equals 1 plus a sec theta. Equation 2, y equals 2 plus b tan theta. Now, if you've looked at Pythagorean identities before, hopefully you'll recognize that sec squared theta and tan squared theta, if you can get those two trig functions on one side of an equation, it's possible to eliminate them. Or to not just eliminate them, but to replace them with a nice whole number. Now, recall that cos squared theta plus sine squared theta equals 1. So that's our fundamental Pythagorean identity. If you divide all three terms by cos squared theta, you end up with 1 plus tan squared theta equals sec squared theta. Now, if you subtract tan squared theta from both sides, you end up with sec squared theta minus tan squared theta equals 1. I've also switched both sides around too. So I've taken this positive or plus tan squared theta, move it over to the other side, becomes minus tan squared theta, and just swap the sides around so that you end up with sec squared theta minus tan squared theta equals 1. Right. So somehow we need to modify or rearrange equations 1 and 2 so that we end up with sec squared theta and tan squared theta being the subjects of their respective formulas. All right, so from equation number 1, okay, we have 1 plus a sec theta equals x. So I've just swapped both sides around there. Moving on, and just to save a bit of space, I've written the solution sort of across as well as down. So a sec theta equals x minus 1, so that's just subtracting 1 from both sides. And finally, dividing both sides by a, and of course a cannot equal 0, we end up with sec theta equals x minus 1 over a. And let's call that equation number 3. Now, in a similar fashion, equation number 2, we're going to sort of do the same thing. We're going to make tan theta this time the subject of the formula. So from 2 plus b tan theta equals y. Subtracting 2 from both sides, b plus tan theta equals y minus 2. And then dividing both sides by b, and of course b cannot equal 0. Tan theta equals y minus 2 over b. I should write down here somewhere that a, of course, cannot equal 0, and b here also cannot equal 0. Okay. Now, we have our sec theta and our tan theta as subjects of their respective formulas. So, but we need sec squared theta and we need tan squared theta, because that's what we're going to work with. Okay, I'm just going to move the board up a little bit. So I've written the second half of the solution in blue. So now from equation number 3, so that's our equation 3, we need to square both sides. And likewise, we're going to do the same with equation number 4 as well. So squaring both of these equations, so from 3, sec squared theta equals x minus 1 all squared over a squared. So a being on its own, sort of in the denominator of the fraction, I don't have to put it in the brackets, I can just square it and leave it outside the brackets, of course. And then I just switched both sides around, so end up with x minus 1 all squared over a squared equals sec squared theta. And likewise, equation number 4, we have tan squared theta is equal to y minus 2 all squared over b squared. And just swapping both sides around, so left hand side and right hand side, end up with y minus 2 all squared over b squared. I might just draw that vinculum a little bit longer there. Y minus 2 all squared over b squared is equal to tan squared theta. So now I've got it in a form that I could now eliminate sec squared theta and tan squared theta by subtracting one from the other. Okay, so this is based on this identity here, this Pythagorean identity there. Okay, so if I take equation number 5 and I subtract from it equation number 6, you'll have a sec squared theta minus tan squared theta. On one side of the equation, I could replace that conveniently with the number 1. So equation 5 minus equation 6. So subtracting one left-hand side from the other, respectively. So x minus 1 all squared over a squared minus y minus 2 all squared over b squared is equal to sec squared theta minus tan squared theta. So sec squared theta minus tan squared theta, and of course the two left-hand sides, x minus 1 all squared over a squared minus y minus 2 all squared over b squared. So you end up with, or now on one line, x minus 1 all squared on a squared minus y minus 2 squared on b squared is equal to sec squared theta minus tan squared theta. And we know that that expression there can be replaced with the number 1. So therefore, x minus 1 all squared over a squared minus y minus 2 all squared over b squared is equal to 1. And that is our Cartesian equation that corresponds to this set of parametric equations. Okay, don't forget also that a cannot equal 0 and b cannot equal 0, and it's very important to state that. Thank you very much for watching.